the special unit of Quivers and their 3D mirrors. Mainly based on the work on that work. And the Quiver meeting given by Chunhao. And one of the authors of that work is here.
Oh,
two of them.
so we have experts.
So the idea is that for a theory, you can get the mirror theory where the Coulomb branch and the Higgs branch are interchanged, and this is called a 3D mirror pair, and a lot of them are constructed by D3 and D5 and NS5 brain systems. And in those brain systems, you can do the Hanani-Witten transition and then use S2 to get the mirror theory. So, and most of those examples are gives you a quiver with unitary gauge nodes. So one of the most well-known examples may be something like just a linear chain of nodes with some flavors on it, and this will due to another linear chain of unitary nodes and with some flavors on it. And then a question will be, what will happen if we change some of the nodes from unitary node to special unitary node? So for example, we can change all of them into that. So for example, we can change all the unitary nodes into special unitary nodes, and or only some of them, and we will see the answer will look like just changing those flavors into some U1 nodes and some connections between those U1s and those unitary nodes, maybe connections with multiple links, something like this. So I think we can start from some examples and see what will happen in the brain system. So going jump. Let's start from an example of this. I do two nodes here, and the brain system for those quivers should be something like this. And you can do well, let me show you. Let me draw the unframed quiver here, and you can do those conditions of this brain system and recheck some configurations like this. Here the crosses are D5 brains, and those vertical lines are NS5 brains, and those horizontal lines or D3 brains, the same here. And we can read off from this brain system, the mirror theory is read the unframed version. So then what we want to see is what will happen if we change every node into special unitary nodes. For example, we use this. Then we need to we need to color those NS5 brains. And if a node is SU node, then change the color. So this will have maybe one more color. Let's go the last one at this. And then the D3 brains are as before. And then we can do the transition to reach at this phase. Here we have those brains here. And now we interpret this brain system as giving the quiver of the yeah. Those two should be different colors, but because we don't have more colors, so I labeled them as black 1 and black 2. And the way to interpret this is so in this picture here, those 6 brains, we think of them as heavy degrees of freedom, and they cannot move, and they give you a flavor of as you see. But if those brains are colored like that, then they will give you dynamic degrees of freedom like this, and they can move separately and independently. Gives you those U1s, and they are connecting to the U3 here. And then the next rule is so we will have each color gives you a different U1 node and the intersection. The intersection between the color the NS5 and the D3 gives you the number of connections between the U1 node and the gauge node given by the D3 brains. And there is one more rule. Because we said that SU will change the color of the NS5 brains, and we also say that require that you node not change the color. So now we will get that this theory is the 3D mirror of that theory, and which means the Coulomb branch of this theory will be equal to the Higgs branch of that theory, and the Higgs branch of that theory will be equal to the Coulomb branch of that theory. So we can also change only some of the SU nodes into we can also change some of the U nodes into SU nodes. So for example, we can change this here. This is user, and we apply those rules. Firstly, the SU will change the color, so this color is changed, and the SU will change the color, this color will be changed. But the U doesn't change the color, so we use blue again here. We'll get something like this. And now we only have 1, 2, 3, 4, 5 U1 nodes, and so the mirror should be this. But the intersection between this colored NS5 brains and the D3 brains is 2. So here it's a double link here, and those two theories are mirror to each other. And by applying those rules, the most trivial example is just every node is U, and we see that it will recover this result here.
How can you choose those colors? Why now you have to?
It's just a rule that if a node is SU, then you change the color. If a node is unitary, then you keep the color the same.
Okay, so you can have as many colors as
Yeah.
As many colors as you want, I see.
Well, that's correct. Some kind of additional degree of freedom on the
Sorry?
some kind of additional degree of freedom on the NS5 brain.
Actually, I don't know how to interpret those colored brains from a physics point of view. Well, I just don't understand why those colored NS5 brains will give you 8 degrees of freedom. Yeah.
Those are your question. When you do the interpretive calculation, this one should not allow the incident to be enhanced. but there has to be some interpretation chart. Okay, so it's not like something that they should be.
But instead of giving that, doesn't apply out of the gauge.
Hmm?
You cannot have.
Yeah, this is
the
A-type quivers, and it's also possible to do BCD type.
But the rule don't work there.
What?
Suppose you have
Um,
as maybe type D,
mhm,
and then you have two colors in left
mhm,
and two as two as you.
mhm.
And you
Oh, let me show you an example of D-type. Mhm. For example, one flavor here and one flavor here. But if we want to look at the D-type quivers, then we need to introduce oriented fold planes, which will result like this. Hmm.
you always leave your here from the left to the right
Mhm.
to change the color. What happens if you have, for example, some line type D? So
Example,
you have on left to
just add one more oriented fold plane on this side.
But you make an assumption that we lose the freedom from the.
you always have
It doesn't matter.
Okay, what do you want?
so the two line of the clear when there is the bronze. They have just the same color in their one and the five. The question of if the two things coming in about that year, they need to agree which one is right.
It will not change the.
I understand because for each age of your period, you assign a five grain, right? But when you have, for example, two on the branch of the period, you have completely. I use just
Yeah.
assign 1 and 5. The red one.
No, so for this thing here, we do something like this.
Yes, I'm asking what is the red line, you know, what corresponds to.
File free, and you can draw the link. So we do something like this. Yeah. So these reference between these two gives you this SU3 node, and these two D3 brains gives you this node, and those two D3 brains gives you this node. Does this answer the question?
Yeah.
Ah, okay. And for the flavors, there is D3 brain, and this D3 brain and the strings between this D5 brain and those D3 brains gives you this flavor, and the strings between this and these two gives you this flavor. Yeah.
Should never go back to the same color, right? But starting with a given color,
Mm.
you go to the same next color regardless.
Yeah, never going back to
So it's like
the
some
same
linear
color.
ordering of colors or something
Yeah.
like that, I guess.
Yeah,
And
but
as Tiziano was saying, if we had an affine type A, that would be a problem if we had a cycle, because if we
mhm.
had any SUs and we got back around, we would be at a different color range.
I
That
see.
was a problem. But for the as long as there's no cycles, I guess.
Mhm.
Not this makes sense.
I see. Yeah, maybe a problem. I don't.
If you have an affine type A, so you have a cycle, and you have some SUs in there, then you will change color, but then you won't get back to the same color because we're not, unless we're working colors modulo some S. Well, I mean, we changed color, we went out of color, we changed color, and then we went around, we got back to the same vertex again. But unless we say that colors are modulo n for some n, we can't get back to the same color. Right, I mean, like, take like a triangle with 3 vertices and put at least one SU in there.
The color is not the particular thing, it's just the name to distinguish it. It doesn't matter whether they are doing from the circle. The most important thing is the unity.
I see. So it's not, the color is itself not important.
There's no significance. You can add like a single SU on the cycle, because like it means that you change color once, that's when you go back.
Yeah, that could be a problem, right? Yeah, that would be, I would think that would be a problem. If you have a odd
mean,
number, an odd, but this is
something like this.
this is
and
also an
then,
odd number of SUs. Yeah, if you have an odd
We
number of
need to
SUs,
change this color here once because of this value and change the color one more time on this. But this not, but then the color between this and this are different, which should give you as you instead of you. Right, is that the?
right, so if you have just a single SU, I guess, Pierre was saying. Just a single SU on the triangle and all the others are U. Then, right, then you have these 2 colors are different around the SU, but then they're the same everywhere else. So maybe that would seem to be an issue. Right,
Yeah.
consistency issue. So maybe you need to have at least 2 SUs
Yeah.
for this to make sense.
Yeah.
I guess what we want to do is we want to break the circle into pieces. So what really the color is doing is you want to break the circle into pieces. If you're just a single SU and you cut the circle into a single point, it's still all one piece. I guess this is the issue.
Yeah.
We have to be sure it's going to be, and we don't want to be very important. You could go ahead and do it, see whether we can follow. I still don't see the point.
Just put one single, but put a single SU2 and make the others U2. Or just a single SU2. And now if we want to compute the thing,
And
yeah,
because this is a U2, and so the color doesn't change. Because of this is another unitary, so the color doesn't change. Which means the color between this and this are the same. But as you should change the color.
yeah.
That is the problem.
Okay, what is your proposed paper?
Yes, this one.
Well, not the mirror.
For the mirror. So if we had just unitary,
So this is and
ah. You should be able to do that, right? it seems quite symmetric, because if you're putting, there's this twos, but this is fine, so we have this two D3 branes going all the way around. And we're just alternating an S5 and D5, right? So it should be self-mirror, right, normally. Except
Yeah, if it was all of the.
they're all
Yeah,
unitary,
if
it
all
will just be
unitary should be
self-mirror. So
If, this you. Introduce this,
In an evident solution, you can change the order of the NF5 prime, or you keep them. But I think if you don't change the order of the NF5 prime, you have no problem like in defining this difference as being local property. So if you don't exchange the order of the NF5 brane, so it's an order say the same, or you just move the different brand, so you have no technical problem by saying that the difference of color or just some local property and I don't know what I. You can just say that it's a property of interval.
Don't know.
I see, so maybe we don't entirely know how to deal with this, basically you want to take the mirror exactly the same as if you had just unitary and no SU. But then based on where you had the unitaries, you want to
Just go ahead and complete it.
well, I know how to compute it when they're unitaries,
Yeah.
then it's the same quiver. I don't really know exactly how, I've just seen this about the series, I'm not sure how you're supposed to compute it when it's special unitaries.
It's the same one that you have. What will you find as
Because those branes
so what? You just go ahead and compute. Just ignore the fact that it's funny. Can you draw the brain system? Yeah. Okay. It's like this. Which one is that?
Yeah.
Remove this. So what I understood so far, all I've managed to understand so far, hi, is that if you have a quiver with SUs and U's, first step to find the mirror is to pretend that they're all unitaries and find the mirror quiver. Second step, if you can, because this is not always something you can do, right? But if it works, you can. So if it satisfies a certain property, you can do that. And then once you've done that, now which I guess will always work under, essentially always work in the finite type A case, but not.
Are you drawing the same
Like-
configuration as you had before?
Because you are saying it's self-new.
But the big brain stuff that you had before. Now you have the photo.
Oh yeah, we had only 3 before, not 4. That's true.
It's because it's on the circle
Right.
and
Find the first and last.
Yeah, because we had 3
Yeah.
brains before.
Okay. So the first and last would be the same thing. They're not going to be different from it.
No.
but then how do you realize this as you?
It's pairwise, so you need to do every pair, whether you lock them or it's a local approach. The notion of colors is misleading. The way you frame it as colors is misleading. Just say whether they are pairwise or locked or not.
So these two are locked and these two are locked, but these two are
Yes.
Not
not
locked.
locked and
Ah, so I need to understand this notion of brain locking instead of color.
Now you compute the row. Compute the intersection. I mean, still x's are the same as before.
yeah.
Okay, so now we need to reverse the work.
Yeah, we need to do the S duality, right?
Yeah. Just use most of the footprint out.
If you just
Then you can leave them where they are, just have to swap X's with the lines, right? We have to do the S duality.
And since the frames are locked, they provide a framing to two different modes. Two of them, that's not the problem. But the joint figure should be 50 and 2.
Yeah.
But the framing is different, right? Because two can be.
Yeah, I see. Because
Two of them.
those two are locked together. So we will have this. And these two are not locked together. So they will something like this.
Yeah. And now you need to perform tests whether to see whether it makes sense or not.
So how does you draw this D3 brain on suspending between this D5 brain?
I guess you can go into
But why you draw it like this? Okay.
why not?
In this particular example, it's not,
Yeah,
in general,
but I don't understand what's the
Because it's quite confusing for me. Like when you draw the mirror picture, you still the thing is that like, you just move those D5 brain on this D3 and that's it. Why
yeah, yeah.
why don't you draw it?
Don't
Does
think
that
it
mean-
make a difference.
for this particular example, it does. But in general, it makes it.
Yeah. Okay.
I see.
Yeah.
Good.
So I don't understand though how this locking works. So the locking was if you have a unitary group in the middle, then you say that the two NS5s stretching these brains corresponding to unitary are locked, that you're saying. And if it's SU, then they're not locked. Is that what you're saying? Is that right?
Unitary is locked.
Unitary is locked
Yeah.
and SU is not locked. But now when
Yeah.
we do S duality, then now we're saying
And the
this
thing
about the
is, like,
framing.
if you draw like this, Chunhao is not consistent with what you have done.
Yeah,
So you better be
it doesn't
consistent.
matter for this case.
But it's not consistent with what you have already introduced.
We need to.
The mathematicians want to know how to do it. If you have more than one choice of how to do them, we need to know if they're the same. But why did you draw two edges there, U1 to U2? Because a priori, okay, so a priori we have a framing one at each of the vertices, which you could also write as a single framing attached to all three vertices. I agree with that. And now because of some locking, you made two framings at one of the vertices and one at the others. Why is that? That's strange. Why did we do that? What does that have to do with being locked?
Is this the end of what you want to present?
No,
So let's move on.
Let's
Okay.
move. I agree with Tommy. Let's move on.
so then those two are mirror to each other.
Okay, these are supposed to be.
Fully, that we will have to test it.
Okay, I just don't understand why, but let's move on. Discuss this later.
Okay, so if we go back to this, B type example, we will, have something like, we do the same trick and, we will recheck with some configuration experience. Before. The middle part of this series. There are four discrete things that between them.
You apply these transitions that we've discussed at some point.
Just move this brain all the way to the other side. And we want to read out the magnetic quiver that corresponds to this two. And we will try to-
I'm not sure if we did the transitions in this case of the orientifold along the NS5, but anyway, you say that.
So-
I'm not sure if we discussed what the transitions were in the case of the NS5 orientifold, but
Well, you just move it to this side.
Oh,
and,
okay.
It's the
it's
same.
the
as
same.
the-
Okay, all right.
Yeah.
I see. Okay. And then it's just you just drew the other side of the reflection. then.
Yeah. And this will gives you, and this gives you. Give you something like this, and those two are mirror to each other. Any questions so far? Okay. And we can also do the same trick river.
I always said it's so it's 4U1 no 5U1
Sorry. Sorry. Yeah. Also,
Okay.
what is the question? Yeah. For this case, no. With the orientable. Yes, yes.
So when we move the X all the way over, then we have these 4 everywhere except right before this orientable. Now we have, it looks like just 2 are stretching, but they're also stretching back, right? So it's like that counts as 4 there then.
You have great relation. So, first 4 of them, the first 10 them. The total by number, becomes 4.
But then we're allowed to turn that into just 4 brains stretching across. It seems like magic because there at the orientable we had only 2 intersection points, right? They sort of bouncing off.
So that's what we're gonna apply. Sure.
I see. So then you get like 4 brains that are coming through but intersecting 2 in pairs there, but then you can just move it off, you see. Okay.
Yes, that I also is not very short now. Yeah.
Yeah. Yeah.
Mhm.
Very number is 4, the whole places, right?
Sorry?
Yeah, the brain number is 4 in all places. Yeah, I agree. So you can represent it, maybe this is not the way you want to think about it, but you could represent it at first as some diagonal brains going across this middle line, and then if you wiggle them, then they become parallel. Well, because they're intersecting here, right? So maybe this is too naive here, but we have this situation here, if we wanted to reflect it as well, okay?
Yeah, can cause that draw the mirror. Yeah, yeah.
And then we would end up having, again, 4 brains, but they would be intersecting in 2 points, 2 of them in pairs, but then we could and if we pretend.
Not allowed to change it. The relation is fixed.
Yeah, but then
So you could think of it as ending from left and then to the right, right? That's the main critical feature. If you deal with the 2 of them end to the left and the other 2 end to the right.
Yeah, it's like the picture I would get here is instead of these 2 being parallel, this one will be going from here to here. This one will be going from here to here.
So yeah, exactly in your sense of like so this 2 so on left right brain it goes to the right hand side brain. There are 2.
Yeah, so this one will go
Yes.
down to here.
And also the other way around. From the
Right, exactly. So this one go down to here, this one up to here, this one down to here. So yeah, I mean, do something like this, right?
No, you don't, you just parallel, you just draw parallel, and you will see.
Yeah.
You draw two parallel and then the mirror.
Just specify where the end.
I see. Because here we had this bouncing off picture going on, yeah.
Yes, I mean,
It's a
this
short-
picture that was like what they did, the end on the left, on the right, on the other side.
I see.
That's an equivalent of like.
Okay. This is bouncing. It's just this bouncing, which is confusing.
Yeah, so if you prefer the bottom picture, that's perfectly fine.
Yeah, I guess the bottom picture
Yeah.
is what the top picture is supposed to
I
represent.
also prefer the bottom one, but it just cost them take more space.
Okay, yeah. Fine, okay. So I think of the top picture as a notation for the bottom picture. All
And
right,
also to there's also another type of
But they say you're reading what you want, the suspicion.
just as before.
Now let's go to the
so why is it an SP2 at this vertex? And why are we getting a SP type when we do the S duality? It's
Because those D3 branes are half branes. So we only have two D3 branes and then consider that P2.
uh-huh. Which brains are only half brains, you see?
Those are all those D3 branes are half branes.
Ah. The D3 brains are half brains, you see.
Yeah.
But there's four of them. Four half brains, you
The
see.
red full uses the projection. You have the full matrix with the projection.
Yeah.
The transparency is equal to the
I see.
So the full physical point is that those three brains pass through the wind plane. So you get the projection.
So it's the question about the type of the group or the rank
Yeah.
of the group.
Yeah, the type of the group
Ah,
and the rank of it. The rank you're saying is coming from this half brain picture.
Yeah,
And the type,
Type is because of the type of the orientable plane is minus.
oh, I see. We did this for the oriented fold in the D3 direction before. Yeah, you can do this also.
Yeah, but the difference is yeah.
Have you seen such a configuration with the real problem?
No, I don't think so. And we did the, when you
Yes, so we
mentioned
have
it,
to specify the rules for those things. So, you have the two types. And you could specify, you can specify. So, Chunhao, if you have one, it's better to do the fundamental basics. Or if we read the Quivers from the plane,
the point is that when we had the original quiver was type D. So there I could understand, I think you've mentioned to me before how to go from a type D quiver to this oriental fold. But now, after we apply this S duality, it seems like, in some sense,
you have four types. You
Yeah.
have the D, C, and D. And there is the electric one, there is the magnetic.
so oriental fold along the NS5 is the same as oriental fold along the D5, because when we apply S2L, we would be changing the orientifold along the NS5 direction to along the D5 direction.
It's similar, there's also the Lagrange duality that you have to take into account.
Oh, I see.
It is similar.
I see, okay. It's tricky then. So you have a whole prescription for how to do all of these.
So you could write the VB. Yeah, T. After the property. And B and C.
D. And
This is B,
D. And
C.
D, C.
Oh,
So there are four labels that we put on the input. On the condition we put anything.
Yeah. Oh, very no notes, but on this hip.
In the here for simplicity, we took the case of the token. We have B and D. And that's the reason for the multiplying, since it's D and D, we should choose B1, choose B2.
Here should be D type.
This is fine, but the timing, should be pretty. Because you are next to another project.
You mean something like this?
So for one, we have the but that's the reason I was asking.
Yeah, I see. Yeah, if it's higher rank, then it should be D type. Yeah, I agree. Yeah. That's
But since always have been seen this thing, I think it's much more important to work the details from Vinta to establish this, and they should link the discussion.
I haven't seen the, we had the two sessions on the orientifold in the horizontal direction. But for the vertical direction, all I knew is how to translate the type D quiver.
Yeah, I think it would be good to complete the zero of the SP. This is the thing that shows up in the web of the 10% of user time.
Ah, okay. Okay, yeah, so, all right,
So let me do it quickly. It's not a difficult extension.
okay. And then we can get back to it.
So when you have an oriented like that, and you choose to use a minus. We will do it like he was choosing the weather. And now collection of like that. This is the configuration. The quiver is of the type SP2K. That's the number here. And again, the projection is such that this is minus. Also, if this is minus, then that's the quiver. And the training is SO2. Yeah.
And now I want to move the brains. In this picture, the stretch between an S brains. This is the S. This is the 5. This is the 5. Those are the 3. And I want to move the 3 brains to stretch between the D5 instead of the NS. That's the magnetic field. Okay. So the way I do it is to take those guys here and stretch. I have 2K of them. I'm going to stretch them one at a time like that. So I need that the number of brains n here will be at least 2K.
Oh,
So if I do this, after that, what I will have, using brain annihilation, I can move them 2K steps.
okay.
If I do that, what I gain is that here there will be all of those values will be gone. Here, one of them will be left. Here, 2, and so on. Okay. If we take the case of 4, for example, you can see that here there are 4 of them. Here there are 3, so 1 is left, and it's 3 to move. Here I have 2 left. Yeah, 3 to move. Here I have 3. And so the exact quiver will be 1, 2, going all the way up to 2K. And maybe I'm just but it would be 2K and 2K minus 1. The last step, you see that after moving those 2K times, I'll have a framing on the node which is at the 2K position. So this one will have a framing. F1. And now the remaining brains will have 2K from there. That's those numbers. 2K. And it is in such a way that the last 2, so in the last 2, let's go what happens in the last 2. So those are the last 2. And I have 2K of them. And I'll do the split that he was using all the time. K of them will go like this. And the other K will go like this. Such that, again, the brain number is K will stay here and 2K over here. Okay, so this will give me this thing. Since I started with the Dn and the algebra is Dn, the total number of brains here is n. So total number of nodes is n, and this is the dual. That's the quiver we showed up in the work of Henderson and Nikata.
So this diagram with this x's is saying you're going to perform these. You are going to perform these Hanani-Witten transitions to move the x all the way over or something. Like.
Yeah, I have to do it 2K steps. 2K steps, and along the way I lose the brain in each segment. I lose them in this way. Then it ends after 2K steps. It ends on the 2K segment. So that's why.
I see. This is a way of getting freeing the x. It had all of the D3s before. Yeah. And now you're performing these transitions, whatever, to get rid of them, to make it just free.
After the transition, it looks like this: 1, 2, 3, it's on 4, and then it ends on
It's
the
just free.
face step. And it's free from all of them. And provides framing. Then you continue. You continue as if there's no other stuff.
Oh, I see, because of
Except
the
for the last
reflection. Because of the reflection, or
So the reflection affects only the last two nodes,
I
and
see.
that's the reason you get this split. This is the D-type ending that he was writing over the. Okay.
I see. This is why it's important that the n be bigger than k or something like that.
The n should be bigger than 2k in order for this to work, otherwise we have to do more cases.
Okay, okay. So then at the end of the day, your chart says that this original one is this type C, this T2 SP of 2k.
Yeah,
The new one,
it's a framed DN diagram. I end up with a framed DN diagram. Where n is the number of it's the framing that I pick over here.
and you see on Licata and Henderson, they found this type D quiver, you're saying?
Yeah, they were computing slices at the top of an SP
I see,
diagram.
I see, which is what I guess you would predict here as the mirror to this orbit closure, which you're getting
By
from the I see. You have the Kraft Porchesi, which identifies this one with some orbit closure, and then you have the Lustig Spaltenstein, which is supposed to tell you which slice it is, and then they actually found there was the slice.
yeah.
All right. Okay.
So now by complete analogy, instead of having the B ending for the quiver, you could do also the B and the C.
Hmm.
And you will get similar thing. We cannot call them quick mirrors and more because we don't understand the academic without the necessary. But we could nevertheless complete the quiver.
I see.
So this you have not seen before, right?
No, I mean, you mentioned this example, I guess, from the Henderson and the Kata before, but I didn't know how to do it with the brains. They just call this a frayed type DN or something, a framed type DN. Framed.
Yeah, it's a slant from the fungus one.
Okay. Okay, and the framing is at this 2K. Single framing. All right. Yeah, so then we don't have to look up the chart for the result because the resulting thing is just unitary groups, because nothing is it's unitary groups as long as you don't have any brains, any D3 is stretched between things which are mirror of each other. If you do that, then you need to use this chart. Otherwise, it's just unitary.
Yeah.
Okay. All right, great, thanks.
Looks better. Yeah.
Now you could just check the photo and the cycle of the expansion including the each result or how full computation can be. And so make sure that
That's true.
And one more thing I want to say is that we can also do this trick reversely. So if we start from a unitary quiver, for example,
We're gonna do something rigorous.
And with some heat of new and actions. And we can use the same trick but reversely, and then get the mirror, which is
Over in reverse, you're saying, okay.
yeah,
I thought you were saying you're gonna do the same trick rigorously.
reversely.
Reversely.
Sorry, reversely.
All right. Perfect. Oh, yes, okay, yeah, this is,
We start from some unitary quiver with some U1 nodes connected to them, and finally we get that result.
this is going to include this
Which is,
example that you
yeah.
explained to me using type S quiver before.
Which can, yeah. Well, this can also be seen from some other techniques.
Right. This is a good, this seems
And for example,
like a nice
also start
technique.
with something like this. And you will get
Which one's the electric ones and which one's the magnetic ones there?
it doesn't matter. It just mirror to each other. What okay. Yeah.
Right. I see. This is great.
And
It's another way to get this, having the class, this class S point of view, whatever, we had just U1 and U2 in the middle, then we were getting, instead of SU2, we were getting SO3. No, it's almost the same. Almost the same thing. Yes, okay. To this covering.
yeah. And we can also do the same trick with maybe minus tilde oriented for plane here, or one plus oriented for plane here. But then the
Maybe some, you know that angle is also.
Which particular case? Not too much, should have, maybe more.
Because it is the implosion of the control.
I see. You know, that, no, this last example, what's the
Last example,
1, 2, 3, 4?
place for
Because if you did unitaries, we would be getting the nilpotent code. We took all the unitaries, turned them into special unitaries, so we're taking a partial reduction, I guess you could think of it as doing something that if you take a further Hamiltonian reduction by 4 torus, you get the nilpotent code. And now, on the dual side, it's the other way around.
if you want to trade the capital quotient by 1 billion to capital quotient by 3 billion. So we say that the need to control is the hypothetical, the force reduction, total this reduction of some space.
Right,
And this space is given by a Coulomb.
that's right, yeah, so it is the Coulomb branch of the, I see, okay, so you still have to know what this Coulomb branch is, I guess, but if you're happy with that,
It's very complicated space, it's not an easy space. But this gives the answer to this question.
I mean, we could have just tautologically just written this hypercalar quotient on the right and said that that is something which obviously has a further quotient to give nil put and call. If he wanted to do something which, I don't know, is it generalized to other types or something, this type of idea, or I don't know.
Yeah, I mean, you could generalize it to other cases, but it's not the main thing. The original question was, and then you can prove it at the same time, then the one that you know what would it be for the other algebra, which are classified.
But I see, but why did he want to use the Coulomb branch here? Because I mean, a priori, you could still just take the Higgs branch and you obviously have something which has a torus reduction to nil put and cone. So what was the point?
And the A type.
For the A type, but in other types, you can, when you can't do that with the hypercalar quotient, you can still take a hypercalar quotient of a Coulomb branch to get a nil put and cone. I see.
Yeah, there are cases from the.
Beyond type.
So,
I see.
so
So I didn't realize this was what was called one of the examples that was called implosion or something. I haven't followed this
Yeah.
implosion very much.
if you look at the work with the Q1, because the bigger portions, and then
I see. All right, that's interesting.
The SP1 there is empty or it has the SU1 there is empty or it has some.
I think you can just think of it as the one shape.
Okay.
And as a byproduct of this coloring shape is that if you start with this, oh, and change this, into special unitary, which means here are two branes are locked together, and the other three branes are not locked together. But then this would be,
But you're only locking neighbors, right?
yeah,
You don't lock brains which are away from each other. And you don't lock the second and fifth brain. They are only neighbors. So the notion of locking is a local.
yeah, it's a local.
When you pick it with
Right.
colors,
Hmm.
you make the impression that this is a global
I see. I see.
restriction.
I see.
It's not. It's misleading.
I see.
The color is just a way to say that either you lock or you don't. That's the point. You either lock or you don't.
Now, what does it mean to lock or not to lock, though?
Uh,
Then, when we're,
Lock just means they can only move together, just like in this case.
When you compute the Quiver data, you have to, they need to add the Quiver data together.
I see.
I think that it's more important to emphasize this point. Like how you compute the Quiver data.
Ah. Okay,
That's the notion of locking.
Mm.
It's with which rebrane do you intersect.
oh, I see, okay. But this was a problem on this example. I don't think that what was written here is correct here. The problem is that we want to lock, we want to lock together two NS branes to begin with. And then if we take S duality, then we're locking together two D5 branes.
It's
But the problem is that these are two D5 branes which are separated here by an NS brane. And we can't get them to be not separated by an NS5, so that's a problem.
Right, and that's the reason we contribute to the same one one frame contributes to two nodes. Because
Ah,
that's what we was going to. When you have two nodes, you have one frame.
I see.
That's the important thing to do.
I see.
When you have looking, either you have one frame that contributes twice to the same node,
Mhm.
one frame which contributes to two different, depending on the configuration.
I see.
And it's always local locking. It's not a global effect.
I see.
So we could find one where simple exercise where we will see how the training works. Do you have examples?
I'm
Still seems a little bit fishy
no.
to me.
Let's first make sure that we understand the finite A. Then after we understand the finite A, we can do the finite. But I think it's absolutely necessary that we first understand the finite A. So maybe we could do a simple example with finite A.
For example, the thing here.
Yeah,
Oh.
well, let's see if we have the question.
If we're doing a Higgs branch, then a priori to me, it makes no difference, right? If we take a single framing of U1 or multiple framings of U1, it's the number that we have attached to each vertex. But that's like the point of this Coley-Bovee trick or whatever.
Right.
So like the difference, so here it doesn't seem to me that the locking would be doing anything if we're taking Higgs branch of this quiver. So we take Higgs branch of both quivers. Yes.
But you can only do it once. You can only do it
Yeah.
once.
Yeah.
There are two new ones there.
Yeah, but they're both supposed to be framed. So.
I believe the one is not.
No, here is
Oh, that one's not a framing.
Not a
Oh, they're not framing, they're gauge.
There is one U1 implicit. U1.
Is it correct that all of your nodes are big?
yeah.
Okay.
Yeah. Or gauge.
Because normally if we take the dual, this quiver, there were no SUs, we take the dual, we would get another quiver, which is exactly the same, so we still have the framings, not gauge.
Yeah, so the College movie will tell you that there is only one node of one, which is attached to all three.
All three, yes, that's right, it's a unitary case, yeah.
And here, as opposed to that, you have two nodes of one.
Oh, I see, okay, so these are both gauge, okay.
And that makes the difference. Now we need to test whether this is correct.
Okay. Well, then I guess I can see that it could make some sense then. So you're using the Coley-Bovee trick, this sort of idea to say that in the locked case, it's just a single gauge node of one, and then in the unlocked case, you separate it into multiple gauge nodes of one.
Yeah. That's why I'm saying we should do more examples until we are absolutely convinced that there is the final thing.
I see. Well, I think we have to get lunch though.
Yeah, just one last comment. So if you start with this quiver, but change this to SU, this should be the same as this, because in that case it's just change the, and they should give you the same thing.
You're starting with the unitaries and turning one into SU, or you're starting with the, okay.
Yeah, so once I turned this to SU, and once I turned this to SU, and they should give the same thing.
You turn this one into SU and you turn on the dual side. On the dual side, you turn the other one into SU, you see. So in this example, all that happens on the dual is that you swap where the SU is.
Yeah.
Uh-huh. You're saying that's what.
But you can also, well, I mean, this should be the same as this, and this should be the same as this.
Okay, say it again, what should be the same as what?
So if you change your, we change this to SU, should be the same as changing this to SU.
Oh,
And if you, this should be the same as this.
I see. Okay, but to see this, we would have to do the computation, I guess, but, okay.
But yeah, with this locking technique, you can directly see it from the brains.
Well, you have, you can directly see it from the brain, to say. Because those SUs there are the, are saying that these NS5 brains are locked together. And then on the dual side, you're saying that the D5 brains are locked together. Right. But once you've written the S dual quiver like that, you put all the D5s over into the framing part, right? So if we say that some of them are locked together and some of them are not, why is that the same as saying that some of these nodes are SU?
Because I think they all gives you the magnetic quiver like this. So for this case here, I think they all give you the
Like, a priori, what I would expect is if we have U1, all U1s and 5, then we get U1s and 5. Now if we unlock some things, then that means we're going to separate the 5 out into multiple framings, but this is not what you're doing.
So you should think of it, when you lock, you think of two objects as one object, but they're connected twice, which is different than having two objects each connected.
Right.
That's the difference. Right, so in the previous case, you have 5 nodes of 1.
Right.
Each one is individual. In the second case, we have 2 objects which are not. And both of them are contributing, but since they are one object, they belong to
But just to make sure I understand, so this is the mirror to this. Right?
Yeah.
And if we do this one, I thought you were saying these two were mirror
those
to each
two.
other.
No. I think those two are the same because both of them gives you the.
Oh, they
mirror
both
of
give you the same mirror. I
Yeah.
see. Oh, I see.
That's okay.
That's the thing. But this is not something you can see directly. They should be the same. Because
Completely.
you can see something that maybe, I guess you have to be able to do it without using S2LB as well.
There might be some ways to identify that they should be, yeah, like the same things included.
I think it's the fact that the new ones are engaged. If you look at the pattern of the U1, the top one is 1, 3, and then the bottom one is 3, 1, so it's the same. You have two examples of the two ones that go some of the same. You asking a different question.
You mean it's just a difference of where you engage the U1?
Yeah.
Mm.
Because the other ones form the same. There are sort of 3 U1s that you are engaged on the other ones, but they have the same relationships to each other. And when 2 U1s are adjacent to each other, they can be switched as long as you don't mess up the ordering of the other ones.
So the bottom line is that when you have this locking thing, the number of edges remains the same, because the planes are the same way.
Yeah.
It's just that the number of engagements changes.
Yeah, so for example, here it only depends on a partition of 5.
Maybe I get lunch then.
Yeah.
Thank you very much. Thanks, Chunhao.
Thank
That's
you.
great. So